G, and delta H, delta S, and delta G. Free energy, which is noted by the symbol G, is really a relationship between randomness and temperature, as you can see here. A process is spontaneous in the direction in which the free energy decreases, or negative delta G. Negative delta G means positive delta S of the universe, because if free energy is given out, the universe can take that energy and become more random with it. Delta G equals delta H minus T delta S. This is that relationship that combines delta G, delta H, and delta S into one formula. Remember that temperature has to be in Kelvin. Let's look at this question. A liquid is vaporized at its boiling point. Predict the signs of delta H, delta S surroundings, and delta G. Well, if something is vaporized, that means it goes from a liquid to a gas. And you have to add energy to do that. So if you're adding energy, it's a positive delta H. What's happening to the system in delta S? Liquid to gas, more random. The particles are able to move more freely as a gas. If the particles are moving more freely, the surroundings must be losing randomness. And delta G is 0 here because it is at the boiling point, which is true. Delta G is at equilibrium. The value of delta H vaporization of a substance X is 45.7 kilojoules per mole, and its normal boiling point is 72.5 degrees Celsius. Calculate delta H, delta S, and delta G for the vaporization of 1 mole of this substance at 72.5 degrees Celsius in 1 atmosphere. Now, you might think we don't have enough information to solve things here. Well, we do have the delta H, which is good news, so we can use delta G equals delta H minus T delta S. Temperature we have as well. We don't have the delta S, but luckily for us, because it's happening at the boiling point, we know delta G is 0. So we plug in 0, and we plug in the delta H, and we plug in the boiling point in Kelvin, we can solve for delta S. The thing to notice is, you will see that the delta S is 132 joules per Kelvin times mole. The units of delta S are in joules per Kelvin. The units of delta H are in kilojoules. So you have to make sure that when you get an answer, you put the correct unit, which means you'll have to convert to get to joules when you solve for delta H. You'll notice delta S is positive here. What about the delta S surroundings? It's going to be the same exact value, but it's going to be negative. And of course, delta G is 0. That's how we were actually able to solve this particular question. Remember from intro, if delta H and delta S are certain signs, then we know if the reaction is spontaneous. The first situation is one where delta H is negative, which is favorable, and delta S is positive, which is favorable. So this happens at every temperature. The last situation are both unfavored. If they're not favorable, this will not happen at any temperature. And then the other two situations are ones where either delta H is favorable and delta S is not, or delta H is not favorable and delta S is favorable. These are the maybe situations. These reactions can happen at specific temperatures. If the two factors for H and S are positive, it happens at high temperatures. If the two factors are negative, it happens at low temperatures. That helps me remember it because high numbers are both positive. Low numbers tend to be negative. So that's how I remember if it happens spontaneously at high or low temperatures. And of course you'd have to calculate when delta G is 0 to figure out the temperature at which there's some sort of equilibrium or a change in the spontaneity of the reaction. The third law of thermodynamics says that the entropy of a perfect crystal at 0 Kelvin is 0. That means molecular movement stops. The entropy of a substance increases with temperature, so anything above absolute 0 has molecular movement, even solids. And we're going to look at some standard entropy values because we can calculate delta S just like we did delta H. Delta S0 represents the increase in entropy that occurs when a substance is heated from 0 to 298 Kelvin at 1 atmosphere pressure. Here's how we get it. Products minus reactants. So delta S of the reaction is equal to delta S of the products minus delta S of the reactants. So if we had a situation like this, and we wanted to calculate delta S for this reaction, and we're given the following information. Again, notice joules per Kelvin mole. These numbers are plugged in. Make sure that when you look at sodium, which is 51, you multiply by 2 because it's 2 moles of sodium. Water is 2 moles of water. Sodium hydroxide is also 2 moles, and hydrogen is just 1 mole. Products minus reactants, in other words, we're going to take whatever 2 times this one is, well, 100. That's what these are, the products, and these are the reactants. These, of course, have to both be multiplied by 2. And when you do products minus reactants, you can calculate the delta S value, which they say here is negative 11 joules per Kelvin. Remember that delta S, the standard units are joules per Kelvin, and the units for delta H and delta G are in kilojoules. So sometimes, not here, but other times you may have to convert when you're plugging in.